So let's start. Some more examples. Actually, kind of easier example. Something in characteristic 0. Such a, okay, so of course it goes to, okay, can be, this is nth prime, with natural order. Okay, so it's actually, I remember, because I couldn't solve it when I was first year student, to show that this is, well, infinite extension. In other words, show that these elements are even linearly independent over Q. So you have to, so it's a bit, so it's good to give it as exercise before Galois theory, because students cannot do it, but they see how, when does it stop. You can do it up to 4 elements, just by raising to power, and then with the 5th one, I think you really need Galois theory or something. Oh, yes, okay, it's a good. Okay, sometimes some students, I remember, were kind of inventing Galois theory on easy level to solve it. But it really, because it's easy, it's just maps plus minus. But still. But anyway, it is infinite Galois extension. And then Galois of this. So by definition, okay, it is inverse limit. Okay, let me now write, may look strange, but P1 is 2. Okay, and then if you know it always grows, this group must be C2 to the n, so nth product and the maps are projections, and then actually it's quite easy to see that if you have such a system which comes from finite products and projection, inverse limit is the infinite product. I don't know. Well, so topologically, Cantor set and here it's a bit funny because this is so each element has order 2 or 1. Okay, so such a product, kind of infinite product of vector spaces, is not a vector space. You should take direct sum. But it is a vector space because each element has order 2. So it is a F2 vector space as a group of exponents 2. That's always the case because
infinite product is always vector space, but finding a basis is.
Yes, exactly. Exactly. So this is isomorphic. It has cardinality continuum, so it's a vector space of cardinality continuum. So it is isomorphic to this. But the isomorphism is non-constructive to find the basis. But now, okay, but now look, you have this basis, which has continuum elements, so any subset of bases gives you a different subgroup, or a different subspace. Just generate subspace by this subset of a basis. So it has 2 to the continuum subgroups, or F2 subspaces, they're the same, but only to only continuum closed subgroups. Because their mass corresponds to subfields of this. And then really they say what happens on each coordinate, which coordinate you miss, basically, but in this description. Okay? So the moral is that there are, so most of the subgroups are not closed, like many, many more, because 2 to the continuum. So if you pick at random from this, but from this strange basis, then it's most likely, with probability 1, it's not closed.
How did you say that there are continuum and subfields of this field?
But again, so for any subsequence of primes, just generate subfields given by the subsequence.
Okay.
They are continuum. So they are more than count, but still not enough for all of this 2 to the power continuum. Yes, so it's a bit funny that from this countable objects, suddenly we get a group which has 2 levels more, like Aleph 2 or more, depending on continuum hypothesis, subgroups. Okay. Yes, so here my point was to show that it really matters that subgroup is closed, and it may be a rare thing that most subgroups may not be closed. And finally, the profinite group, absolute group of Q, well, it's one may say mysterious. So there is lots of research to understand this group, and part of it is inverse Galois problem. So, which you may state is any finite group a continuous image, maybe even image at all, but I'm not sure, a continuous image of so this is equivalent to the more standard. Does any finite group appear as Galois group of Galois extension of Q?
Well,
No, but the quotients. Okay, there are countably many finite subgroups, yes. That is true, up to isomorphism. Yeah, well, but we have to yeah, I guess people believe it's, not sure, I think people believe it's true, but it's hard to show it. Does anybody, yeah, I don't know. As usual, I don't know much in practice about such things. For example, for a monster group or such strange groups from classification, is it known? So I'm not sure if it's for any particular group, whether people found, or even for particular groups, maybe not. So. So my point here is to say that all of this information is coded inside this group. So if there is a way to understand it somehow by other methods, one could solve this. Yes, so you can see it's much more complicated than this one. Yes, this one contains only kind of as quotient cyclic groups. Here maybe absolutely everything, and also in some complicated way. So yeah, what's happening here is often a big mystery. Okay, so now we get back to model theory. So third part will be this connection. And model theory of finite group actions on fields. So let's fix a finite group. Okay, then we have this language and unary functions, symbols, and we have the theory. LG theory of actions of G on fields by automorphisms. So aim for today and last lecture, so describe model companion. So here the strategy is we will be finding some conditions which existentially closed structure must have, and actually there will be 4 conditions, all first order, which then I will not, I think, have time to show it, also imply existential closeness. So we see how much we need to guarantee that such things are existentially closed. So starting from easy ones, okay, first is perfectness. So a bit of maybe something which didn't appear in your lecture. We have field characteristic. So by inseparable closure, sometimes denoted Fp to power minus infinity, it will be intersection of all preimages, okay, by all powers of Frobenius of F, where this Frobenius is an algebraic closure. So it's pretty formal, but you add all Pn roots of unity, of elements from F. So if it's perfect already, nothing changes. But if you keep doing this, at the end you get the smallest perfect field which contains it. So yeah, this is perfect. So now I'm saying that any lemma, okay, we know that to algebraic closure any automorphism exists, but not uniquely. But to perfect closure it extends uniquely.
What is INS?
Huh?
F to INS, what's that?
Is INS, like inseparable.
Inseparable, okay.
Okay, it is, yeah, inseparable. Because these extensions are purely inseparable. And the automorphism of F extends uniquely. Okay, so that's quite easy. So if sigma out F, then it extends to F arch. But it must preserve this thing. Okay, then let me just see. Yes, because p-th root of something from F must go to p-th root of this image. So existence, so this is existence and uniqueness. It's also clear because for each F there is some n. So a possible value sigma, so let me call it B, so sigma of A 2 power Pn is the same as extension. Because B is in F and it extends sigma, so yes, because there is only one root like this. So lemma also implies that actually any group action, not even finite, by automorphisms on F extends the group action on F ins, because all uniquely extends. So if you want to check whether this still satisfy whether it's action of the same group, like whether group table is the same, you check it because it's the same downstairs. Okay. So then, is it clear that then if F is easy G field, okay, then F equals because we can say if it was not equal, okay, maybe I say something about it. Yeah, because it's like this condition of having p fruit or p and fruit, it's obviously possible to state, and then so this is the easy part. There is one more pretty easy part. So they must be perfect.
I was thinking, can't we say that directly that F is actually equal to F alge?
But it's not true even.
Yeah.
You cannot extend the group action. Yes, this will come. No, then life will be much easier. But look, there is a theorem of Artin-Schreier which actually says that almost you have no finite group actions on algebraically closed field. Only possible automorphism of algebraically closed fields of finite order are order 2 or trivial. So in particular, there are no interesting actions of finite groups really. And actually, I will point out probably on Wednesday that unless if the group is non-trivial, then the existentially closed G field is never algebraically closed. Okay. Even if it's two elements, it's still not good. Yeah, that's another confusing point. For ACFA, it is true. If you look at actions of Z, one automorphism, then yes, an existentially closed field with one automorphism are algebraically closed. So here actually it will be next time. So it's interesting, okay, if they are not algebraically closed, what is missing? And what is missing is exactly coded in absolute Galois group, which is the Galois group of the algebraic closure over it. So it codes all the extensions. And there will be full description what is it. It's a profinite group, and it actually is a profinite group coming from the finite group G. There is a way. So for example, p-adics in this way will be coming from finite cyclic P group. There is a general construction which is quite nice. Yeah, so that's the point, that we're looking at actions of finite groups, but the Galois groups you get are infinite profinite related to these finite ones. Okay, the other, which we call strictness, okay, this name just means faithful action, but in this context it's kind of common name. So definition, a G field K is called strict if the action is faithful. So we could also say faithful. So the non-trivial elements don't act as identity. So I'm saying now that any existentially closed field is strict. So lemma any G field has a strict G field extension. Okay, so it's quite easy. Let's say K. So actually to prove this lemma, I wrote these elements G1, Gn like this, because it will come from the regular action of group on itself. So take variables like in ring of polynomials. So basically you can copy the action of G on itself by the action here. So G acts regularly, so faithfully.
Can I ask something?
Uh-huh.
So the lemma is saying that maybe the G field K has not a strict action.
Maybe it's trivial, even.
Yeah, but you are extending?
Yes.
Okay.
Uh-huh. So if one wants, we could just call these variables by the same elements as G, but it would look strange. Yeah, so this action is isomorphic to action G on itself by left translation. And then this action extends to an action of G on field of rational functions I can permute and then extend on coordinates, but such that on K it extends the given action. I can also do that. So it extends to an action which extends the fixed action. Yeah, so this is this. And of course it doesn't, it's very. And this is strict. So then, as before, if K is a G field, then K is strict. Yeah, because the condition, okay, for lambda G this is something saying if G is not E, that it is faithful. So this is solvable in extension, this one, if G is not E. And this is definitely quantifier free. That's similar to the discussion at problem session. Just this. So actually in the proof, it would be enough, not really even extends to strict, but for any G to extend to something where G acts non-trivially, to see that in existentially closed, all non-trivial G's must act not as identity. Okay, so yeah. So of course the full thing is that solvable means there exists a G extension such that there is an X in this extension, such that this is true. So of course this one and X is one of those. Yes, so this was proof. By lemma. Before some structure. Okay, so that was easy part. Okay, so from now on, our G fields are perfect and strict. Because we are interested in this existentially closed one, in describing them. Okay, so let K such a G field, and let C be the field of invariants. So by strictness, okay, so we have this general result. Okay. Now finite. So if G is a subgroup, which is finite, then such an extension is Galois, and Galois group is exactly G. And strictness basically means this. Strictness means that it embeds. So this is by strictness. Okay, so this is the moment when the fixed group G comes into the Galois picture. It is a Galois group of something of this K over the constants. Yes, so we identify now huh?
I mean, you wrote C over there, but shouldn't you wrote K to the G?
Well, I create this notation I was introduced. So here I use some abstract statement. Okay, that's maybe a bit lazy. But here I want to say that for any G, finite, we have this general theorem, and we apply it to our G, which we can understand as a subgroup by this faithfulness or strictness. Okay, and this is the notation we will use for short. So actually the C is like constants. I kind of like to think about it like somehow automorphisms and derivations. They have similar kinds of model theory. And of course, in the case of derivations, we call similar field of constants, where derivation is zero. And it plays similar role like this field of invariants. That's why somehow this letter C, like kind of constants of the action. Okay. So what to do in the last few minutes? So maybe just the example, which I will use next time. Actually, first I thought, when I first started to think about this problem, okay, I didn't know then what to expect. So I thought, okay, take complex numbers with conjugation, with complex conjugation. So it's like action of group of two elements. It has order 2. I thought first, okay, this is very big, this must be existentially closed, but not. So we see. So we have complex number sigma. So of course order is 2. So this may be understood as C2 field. Of course it is strict, perfect, and even algebraically closed as a field, but still not existentially closed, okay, because it's reals inside. The fixed points are reals, and not everything is solvable in reals. So you have equation x yeah, so this is like the norm, complex norm. Yes, like ZZ hat is the norm. So this has no solution in C. Yes, no element have norm -1. but it is solvable. So I have to invent an extension. So consider, okay, I cannot take any algebraic extension, so take non-algebraic. And it's not difficult, you can send it and send if you do it again, it goes back to x. So this gives. So we keep a complex conjugation on x and do this on C and do this on variable. If you compose with each other, we go back to x. So this gives C2 field extension. Okay, C2 field structure on Cx extending and here of course we have a solution, just this capital X. So such a funny example. So actually like this you can show that algebraically closed field cannot have any finite group action which is existentially closed field, because in any, if you have this action algebraically closed field of group of two elements, element of order 2, then fixed field is like a real field. It always have this property, so the same argument basically works for any algebraically closed fields and automorphisms of order 2. Okay, so this existentially closed G fields will be something else. Okay, so let me keep the mystery till Wednesday when I will tell you exactly what they are. So thanks for today.